All right, let's get started. Everybody got their exam? Yeah. All right. So I don't remember what the grades were, but I think that they were decent. I think for the most part, students' grades went up in the class.
What?
Excuse me? Well, pay attention. All right, well, stop talking.
Damn, you're all tired.
This isn't high school, right? Right? Oh, I'm sorry. All right. So look, grades for the most part went up. People who may have struggled on the first exam actually did okay, so I'm pleased with that. If you're concerned about your grade at all, just get with me, talk with me, all right? After class, before class, I'm in my office also. So we have two more exams, right? Exam 3 and a final. So you have about half your grade in place at this point. The binders are due today, so what I'm going to ask is that if you could, let's just pile them up on that table. So go ahead. What's that? Just take notes on something else, or what do you take notes on a spiral?
Yeah.
Okay, is it easy to get the spiral out of there? Okay. And we are going to begin or continue lecturing today. Yes? Well, I'm going to allow you to go try and find it.
Okay.
Yeah. Anybody else? Binder? Change it.
I'm wearing my boots today.
I hear them.
I know.
Those are the
And
ones
I've
you
got
like?
pants too. On
Nice.
sale. Plus an extra 50% off.
That's always good.
I found them at Shepherd's, but Shepherd's is no longer Shepherd's. It is now the.
Really?
Yeah. This location, I want a bunch of decorations inside.
It's been Shepler's forever.
Now that would be fun. Because it's only for active duty everywhere.
Interesting. All right, 6.1. Look, we have studied what lines, parabolas, which were quadratic functions, polynomial functions, and rational functions, right? And I told you that there were two more types of functions that we need to study in this class, exponential and logarithmic functions. And to start this discussion, we have to first go back and talk about a couple of other properties of functions before we actually address these two, all right? So 6.1 is to talk about what's called composite functions. Or, I don't like the title. Okay, it's called composite functions in the book, but I want you to instead think of this as what I'm going to call functional composition. Now, the difference being that if I say composite functions, you might be thinking, okay, well, we've talked about polynomial functions and rational functions, and this is a new type of function called a composite function. That's not what this is. This is actually an operation between two functions. It's called composition. So if someone gives you two functions, you can add them together, you can subtract them, you can multiply them and divide them. Right? We did that in the past. But there's a fifth operation that you can do between functions called composition. So what we're going to do in this section is we're going to just make sure we understand what it is and how it works, talk about some domain things, and then we'll move on to the exponential and log. All right? That's the idea. So please make sure you understand that we are talking about an operation between functions here. This is an operation between functions, not a new function. All right, let's get going. I think you're going to see this and it's going to look familiar to you. All right? Do you remember this? Given two functions, f of x and g of x, we can find this. So just show of hands. Have you seen this? Fog? Show of hands? Yeah? Okay, so this right here, when you write this down, it's an f with this little o between them. It's not multiply. Okay? It's not multiply. It's of. It's composition. If I want to multiply two functions, I write this. And I don't write the dot. That's implied multiplication between two functions. This is composition.
Wouldn't it also, instead of the dot, wouldn't it be parentheses as well sometimes?
Where? Around what?
The little open circle. It would be f of g.
Oh, yes. Let me write this down. Yeah, let me finish writing this. So what does this symbol mean? All right? This symbol means you take f, and inside of f, you plug in g. I think that's what you were referring to. Yes. So this means you take f, which is the function on the left. That's what we call the outer function. And inside of the outer function, you plug in the g. And that becomes what we call the inner function. Now, let me give you a visualization of what's happening here. We all know that when you have a function, we had a way of doing this it was kind of childlike, but we would draw this little thing and we called this like the domain. Remember this? And then we have a function that maps things over out of this domain into something. Okay, so with this composition up here, what happens is that we pick an x, all right? And that x gets taken somewhere. And it gets dropped off into a new place, right? With the way this is written, x is actually going to go through the g function first. So this map right here, we call it a map, is the g function. So what comes out over here is g of x. It's whatever g does to x. Everyone agree? And that's usually a number, right? You take a number, x, I'll represent it as a dot. It comes over here, it becomes a new number, which is g of x. Then that answer gets plugged into f, right? So we have an additional function here, f, that's going to take this answer and spit it out over here. What it becomes when it comes out here isn't f of x, right? It's not f of x. It's f of g of x, because it's taking g of x and plugging it in and spitting that answer out. That's what functional composition looks like visually. You start with an x, it goes through g first, that answer then goes through f. Understand? This is not multiplication of two functions. So we are going to have some issues here when we start talking about domains, right? When I say this domain over here, this is actually the domain of g, isn't it? It's the domain, it's the values of x that you're allowed to plug in g, right? What comes out over here, we called this the range of g. I said ran g. Do you remember that? That's the range of g. Those are all the outputs. In order for f to be able to work, right, for this function to not screw up on us, we got to make sure that what? That these things here are allowed into f, right? So do you see there's a little bit of a difference in the domain? Like when I'm here and I'm looking at g, I'm saying, look, I got to make sure these x's can be plugged into g, right? When I'm over here, I'm not saying, can these x's get plugged into f? I'm saying, can these g's get plugged into f, right? So that's going to create some issue. We're going to have to address it. When we get to examples, you'll see what I mean, hopefully. But does everyone have a visual of what's going on here? Okay. Now, if we change the composition and we decide instead of writing that F with the little o, we write G with the little o, like this, then the definition of that is the other way around. Goff. You've heard that before? So the first one, I've heard people say fog. I'm sure you've heard fog, yes, because you said Goff. No? No? Okay. So the other one, F of G right here, like this, people will remember that as fog. Because it says fog, and this one says Goff. Right? But I don't recommend you remember it that way, only because if you do it that way, you'll think that those are the only two that are allowed. But when it comes to composition of functions, you can compose any two functions together, as many as you want. You could even do this. You could do FOF. You could do FOF, which would be F composed with itself. You could do F of G of F. So you could actually have composition of more than two functions. Yeah. So let's not limit ourselves to just two, but let's just see the difference between this one and the other one.
It's really easy, just remember
All right, so what would be in the first thing up there? Right here, this is x, right? And which function gets that x first? F gets that function first, or that x first. So F takes that, spits out f of x, yes? And then that value gets taken through the g function and gets spit out as g of f of x. So we have to be concerned with the domain of f, don't we? The things that we plug into f we have to be careful with. And the things that plug into g are not the x's, but what comes out of f. So this is the part that's going to be hard for us to pay attention to. It's easy to say, okay, we have to take these things out and we can't plug those in. But in order to figure out the domain restriction with G, we have to actually look at the output of F, which is going to be hard. Harder. It's going to be doable, but it's going to be more difficult than what we've done in the past. All right. So some language, the way you say this. All right. So F, you see this written? We say, in English, we say F of G of X. That's the way we say that, F of G of X. Yeah, the fog stuff is just cute, but it's not official language. All right, so let's just practice evaluating some composites, some composition, and then we'll start getting into the domain issue, which will become the more challenging part. All right, so here's an example. If I give you a specific function, f of x equals x squared plus 2x, well, let's make it minus 2x, plus 3, and I give you that g of x is 3x minus 4, I would like for us to first, part A, find this. Those would be the instructions given on a test. Find that, that's it. And then the rest of it you would have to figure out. So what I'll do first, since I'm doing my answer, I'm going to do it in blue. I'm going to write down what this means. And this is what this means, right? That's what that means. So the function that was closest to x here, right? The f is further away than the g. The one that's closest to x is the one that x goes into first. And then that answer goes into the outer function. All right, from here, I'm going to write down f. And I'm actually just going to replace g of x with what it is defined to be in this problem. So how is g of x defined? 3x minus 4. And then I'm going to take that answer, and I'm going to plug it into the f function, which means everywhere that I see an x, right, in the f function, I'm going to replace that x with what? 3x minus 4. That's it. So I'm going to write down equals, okay, the f function is the whatever I plug in squared, so it's going to be 3x minus 4 squared, and then minus 2 times, go ahead, 3x minus 4, and I need that in parentheses. Why do I need the 3x minus 4 in parentheses? Because I have to distribute the negative 2 through, right? And then I do what? Plus 3. I change this to a minus 2 right here. Be careful. Yeah. Also, I put the 3x minus 4 in parentheses here and squared, because when you square something, you have to do the whole thing times itself, so the parentheses have to be there. Any questions on where this expression comes from? Yes? I'm replacing this right here is taking the place of the x in the f function. Yep. And now we have to actually multiply this all out and figure out what it is, and then clean it up. And that'll be the composition. So I'm not done. So this equals, so if you were to multiply this out, which means you'd have to do this, right? And do your FOIL. You don't just square each one, right? That's a big no-no. So if you multiply it out, you should get 9x squared, let's see, minus 24x plus 16. That's what you would get if you multiply this all out and collect like terms. I'm not going to show that. And then on this right here, you would get minus 6x plus 8, and then plus 3, which, yes, would give you plus 11. But I'll do that on the next line. So 9x squared minus 30x plus 27. All right. You got that? Yeah, you could factor, but I mean, this is it. This is the function that's cleaned up. Now, let me try and show you, again, visually what's happening here. Let's see if it makes any sense to us how this is working. So visually, what's happening is we're starting with some value x, and that one was going through which function first for us here? It was g? What was the g function? 3x minus 4, right? That's the g function. That's getting spit out over here as something, right? It's getting spit out as 3x minus 4. That's where that point goes, doesn't it? And then that point is going into another function, f, and it's coming out, when you do it all right, it's coming out as this, isn't it? So it's coming out as 9x squared minus 30x plus 27. Yes? So this last one's, if we look at this function right here, right? We look at this by itself. It says all you have to do is give me the x, right? And I'll tell you what the answer is. So this composition, all you would have to do to figure out the actual composition of two functions is just give me a value of x. So let's say I plugged in 0. What would 0 turn into? 0 here, which would be 27, right? Let's check that that's what would have happened. Let's just check. What if 0 went into this function? What would you get? You get negative 4. And if negative 4 goes into, where's f? F I didn't put it here, but what was it? Plus 3, right? If I plug negative 4 into this, you get negative 4 squared, 16, plus 8, plus 3. If you do that, it's 27. Right? So what happens here is this composition actually does all that work for us. We only have to find the composition one time, and then from there on out, we just work with this. All right? Okay. Now, domain. Let's talk about domain of this, because I didn't ask you anything. Are there any restrictions on G? We don't have any division by 0. We don't have any square roots, right? So the domain of G is all real numbers. Is that all right if I use that? well, this is what I used more in class, all real numbers, right? This right here. So I can plug anything I want into G, right? And then I look at f. What can I plug into f? Here was the f function, right? No square roots, no fractions. So the domain of f was also all real numbers. So are we ever going to have any problems with this domain when we switch from here to here? F can handle what? Anything, right? And G can handle anything, can't it? So when I plug something in G, it doesn't matter what number I pick, it's going to spit something out. And that answer, it doesn't matter what that is because F can handle anything. So this is like a really nice composition because there's no domain issues at all. Understand? Okay. So the domain of f of G, right, which would be the composition, is what? All real numbers. Only because the two together was everything. All right, let's do part B. Part B, I'd like us to do the composition the other way around. I want to do G of f of x instead of f of G of x. And let's see, is it going to be the same answer? Are we going to get the same thing? What do you think? No. You don't think we'll get the same thing? No? Okay, let's see. So part B, I want us to find this. Let's find this. So the definition of this, you would have to know the definition of this on a test. You would have to know that this equals G with f of x inside. And then you'd have to know that f is x squared minus 2x plus 3, right? That was what f was? That was given to us in the problem. And now what you're going to do is you're going to take this, and you're going to take the entire expression right there, go to your g function, replace all your x's with this. So what was the g function? Because I've erased it. 3x minus 4? That was g. You're going to replace that x right there with this entire expression. So it should become 3 times, in parentheses, right? X squared minus 2x plus 3, and then minus 4. Everyone see where that all came from? Got it? So this simplifies out to be minus 6x, and then you did plus 9, then minus 4, so plus 5. Is this the same as f of g of x? No? So the composition f of g of x was not equal to g of f of x? They weren't the same? Goff and Fogg were not the same, right? Now the reason I'm pointing that out is because that's actually what we will want later. We want to try and find two functions that Goff and Fogg are the same thing. If Goff and Fogg are the same thing, and specifically if Goff and Fogg both spit out x, then we have what are called inverse functions, and that's what exponential and logs are, they're inverse functions. But we're getting ahead of ourselves. We need to understand how to do the operation first, then we can go check later whether or not functions are truly inverses. All right, how about domain? Are you going to have any domain problems with this? You don't think so? Okay, so let me try and draw. I'm going to draw those bubble things again, but I'm going to draw it without the bubbles. So let's see if you can follow this. X would go into which function first in this problem? F? And what does that spit out?
X squared minus 2x plus 3.
Okay, do you understand that's the same picture without the bubbles? Yes? And then this gets plugged into G, and it spits out this, right? 3x squared minus 6x plus 5. Those intermediate jumps, when I go from here to here, the f function was x squared minus 2x plus 3. And this jump right here, it was 3x minus 4, right? That's what f is. That's what g is. Does f have a domain restriction? No, right? I can plug anything into that. So the domain of f is all real numbers. Then when I get to g, the domain of g, again, because it's a polynomial, is all real numbers. So then what would the domain of the composition be? All real numbers. All right, now the next example I'm going to do, we're going to run into domain issues. This was just to show you how we're going to go about it. Right? On all these problems, you want to be checking domains. You ready for another example? A little more interesting example. All right, for this example, let's say you're given two functions. F of x is 1 over x plus 2, and g of x is 4 over x minus 1. I want us to find f of g of x, fog, and its domain. All right, so what I'd like to do on this is try, if possible, to go around the room again and ask questions, all right? So wait until you're called upon before answering, because I want to give people the opportunity to think through things, all right? I'm going to put a star up here. This is definitely like a test problem, all right? Something you would see on an exam. All right, so let's go. Daniela or Angie, what is the definition? What would I write down here? What would I replace this with?
F.
Okay.
Density.
Uh-huh.
4
Okay, you're going a little ahead of me. I'll put g of x inside. Is that okay? Just to start, right? So that is the definition of fog. And then go ahead. I'll let you.
F from C.
Uh-huh.
4 over X.
4 over x minus 1. Does everyone agree with that? Just replacing g of x with what it is. No questions? All right. Moving along, we'll go to the next table. Anybody there? What are you going to do? Try and explain to me in layman's terms.
So next I would take the function of that and I would plug it into the f function. So 1 over,
You're going to plug it in right there?
yeah, I'm going to replace
Okay.
that x with,
Okay, so you're going to replace that x with this big ugly thing? Right? Okay, that's what you have to do. Yeah, so you start writing down the f function, which is 1 over, right? But instead of x, you've got this big ugly thing, right? So that's going to go in that bottom left corner, 4 over x minus 1. But you still have down here what? Plus 2. All right. Now, do you remember in the beginning of the class that there was a review packet thing that y'all were supposed to do, and it had all these different things that I sent out to you? This is an example of a complex fraction. You need to be able to simplify it. So in order to simplify this, let's move to the next table in the back. Anybody remember how the first step of simplifying this would go? Oh. What would you do here if you had to clean this up? Yeah, okay. Under the 2, yes. You're going to get a common denominator and put these two together. That is correct. So you have to be able to look at this as a fraction like this, 2 over 1. And then realize that, like you said, the common denominator here would be x minus 1. So you have to introduce an x minus 1 on the top and bottom. That ring a bell for everyone? Okay, let's continue this. Look, the first problem was real simple. It was just polynomials and lines, and you just plugged them in. It wasn't a big deal. This is going to require more. So here's where we are. 1 over 4 over x minus 1 plus, how about I write 2x minus 2 over x minus 1. So I just distributed the 2 through like this. Since they have the same denominator, I can put the 2 on the bottom together, can't I? So I should get 1 over, when I combine these, let's see, we'll move Jordan or David. When I put these two together, 2x plus 2 over x minus 1. Everyone agree? And then if you have 1 over a fraction, you can flip it, right? That's what the property of fractions is. So this will just become x minus 1 over 2x plus 2. And that should be it. Yeah, now we have to talk about the domain's going to be the even harder part of this, I think. Do we have any questions on how I got that, though? Yes? This is 1 over a fraction. So you have to recall that, well, I can do it this way. Let me see if you agree. This is 1 over 1 over 2x plus 2 over x minus 1, right? That's a fraction, 1 over another fraction. Division of two fractions is the same as multiplication of the reciprocal. So if you divide two fractions, same as multiplying by the reciprocal. So you flip this up, make this x minus 1, 2x plus 2. And then when you multiply straight across, you just get this. Or you can just remember that any time you have 1 over any fraction, it's just that fraction flipped over. All right, let's talk domain. All right, so where does x go through first in this problem? It goes through g? And g was what function? 4 over x minus 1, right? So g was the first function, and it was 4 over x minus 1, right? Then that answer went through the f function, which was the function 1 over x minus 1. Was it? What was it?
X plus 2.
X plus 2? Everyone agree? This is what g was, this is what f was. When we did all the work, we said this was the result. Yes? Now you might think that all this drawing stuff is kind of childish, but I hope that it helps us with the next step. If I try and plug something into g, right? What's the one thing I can't plug into g? 1. Let's let everyone have an opportunity to at least think for a second. Not everyone has taken calculus, so it's kind of, we want to let everyone have the opportunity to think through the problem. X can't be 1 because you have division by 0, right? So does everyone agree that the x that we plug in here can't be 1? So we have a restriction already. So I'm going to put over here, x cannot be 1 because of the domain restriction on g. Now, what comes out over here after I do the g is this result, right? We need to make sure that this result doesn't screw up f, right? What's going to screw f up if I try and plug in what number? Negative 2? Does everyone see that? If I try and plug negative 2 in here, I'm going to get messed up, right? Yes? But see, the thing I'm plugging into this is not x, is it? So I can't say x can't be negative 2. I have to say that the thing I'm plugging in can't be negative 2, right? This result can't be negative 2. If this result's negative 2, I try and plug that in here, I get division by 0. Do you all see that? It's a subtle thing, but it's very important. Right? Composition, didn't this get plugged in right there? That's what Nathan said, right? You said that, yeah? Yeah. You said when we were doing composition, you said, I'm going to take this, I'm going to replace that x and f with this, right? So what if this thing turned out to be negative 2? That's not going to work, is it? Right? And so that's what we have to ask ourselves on the next step. We're not saying x can't be negative 2, we're saying that can't be negative 2. Okay? So I need to set that equal to negative 2 and solve it. Okay, so that's this first step of the domain restriction is just what we've done in the past. You look at it, you say, what screws it up? 1, okay? Can't be 1. But the next step is the harder one, because it's the output of this that can't be -2. So I'm going to write this down. The output here, I need that 4x, I'm kind of out of room here, but I need that 4 over x minus 1 cannot be equal to what? -2. I need that to be true, right? So let's figure out where it is. And then wherever it is, I will yank that from my domain. So let's actually solve that. Just remember, I want to know where it's not happening, so I'm going to find out where it is happening, and I'm just going to pull that out of my answers. So let's see. Giovanna, or how would you go about solving this?
Would you multiply x minus 1?
On both sides? So you're like clearing the fraction. Correct. You're going to try and solve for x. We have what's called a rational equation here. So you clear fractions, multiply both sides by x minus 1. That should clear you out over here. And then, what do we have? 4 equals, distribute through -2x plus 2. Keep solving. 2 equals -2x. Divide both sides by -2. So x is -1. Yes? Subtract a 2 on both sides. Divide by -2.
I guess I'm a little further back.
Okay.
I added 2 to both sides and then tried to get it. I guess that's all.
Where, at the very beginning?
Yeah.
You could have, but then you would have had to do common denominator or something like that.
Yeah.
This is the easiest way to do this problem because you have the fraction isolated,
Okay.
and so you want to clear your fractions at this point. So you try and clear out the x minus 1 on this side by multiplying both sides by x minus 1. So in working through this, does everyone see that the solution would be x is -1? Yeah? That cannot be allowed, right? We cannot have x be -1. So x here, see, I'm trying to come up here with the domain. The x cannot be -1 either. And there's no other issues, right? This is the only issue we have. G cannot handle 1, right? Couldn't plug 1 into G. And over here, the f couldn't handle what happens if you plug -1 in. So our domain is everything except those two.
So it could be a -2?
It could be -2. I'm going to show us. I'm going to show you in just a second. But right now, I just want to summarize the answer. The answer is this. The domain of f of g is -infinity to -1 union -1 to 1 union 1 to infinity. That would be the answer for the domain. Does everyone see why? That means everything except what? -1 and 1. So you're going off the number line. You're picking out 2 numbers off that number line, -1 and 1. This is a shorter way of writing the domain right here, but this is using interval notation, which is what we've stuck with the whole class. All right, let's investigate again because I really do want to make sure that you understand what's going on here. All right. If I try and plug 1 in right now, if I try and plug 1 in, what happens? Division by 0 can't do it. If I try and plug in -1, let's see what happens. Can I plug -1 in right here? Yeah, you get 4 over -1 minus 1. -1 minus 1 is -2. So this is 4 over -2. What's 4 over -2? -2. And now that's what comes here, and f wants that, right? F is going to get that. And what is f going to do with -2? It's shit. It's going to not be able to work, right? So even though -1 could go through G just fine, it's after G has that, it's what it spits out that f can't handle. Understand that? Now, does that mean, we said negative 2 wouldn't work here, but would negative 2 work if we plugged it in the beginning? Let's see. What happens if I plug negative 2 in for this? I'm going to get 4 over negative 2 minus 1, which is 4 over negative 3, right? Which is negative 4/3. If I take that and I plug it in right here, negative 4/3 plus 2, is that going to give me division by 0? No. So I'll be able to figure out what that is, and it'll spit out an answer. So that's where we have to be careful with these. You can't just look at this and be like, oh, my domain is, it can't be 1, it can't be negative 2. You have to set up this equation in the intermediate step to be able to get the domain. See, that's a little trickier than normal, right? Okay. All right, what about the other way around? What about g of f of x? You think we'll have the same domain? No. You think it'll change? Let's see. I want us to find, for the same two functions, find this and its domain. Same two functions. Let's first find what it is. G, but inside is f, which is G, and inside was f, and I've already forgotten what f is.
1 over x plus 2.
1 over x plus 2? And that gets plugged into the g function. And the g function was 1 over x minus 1? 4 over x. 4 over x minus 1. So this is going to become 4 over, but instead of x, what do we put? 1 over x plus 2 minus 1. Everyone see this? How that worked? Now you got to clean that up. So same thing we just did a minute ago. We're going to get a common denominator. I'm going to rewrite that 1 as 1 over 1. And I'll multiply the top and bottom here by x plus 2. Right there. That way I'll have a common denominator. So I'm going to get 1 over x plus 2, and then you have to be careful with this minus sign, right? This negative. That negative is going to get distributed through each of these, right? When I put these together. So you know what? I'll do it like this first. I'll put minus, and then I'll put x plus 2 over x plus 2. And then on the next step, I'll put them together. Equals 4 over what is it?
So I got minus x minus 1.
Minus x minus 1. Minus x minus 1. So you're doing 1 minus x minus 2, because this negative goes to both. So you're doing 4 over 1 minus x minus 2 over x plus 2, which is 4 over, you said negative x minus 1 over x plus 2. We can flip this again, can't we? Flip it up? Yes. Let's see how we do that. This is the same as 4 over 1 over negative x minus 1 over x plus 2. That's the same thing, isn't it? 4 on top is the same as 4 over 1. Then I'm going to flip. So I'm going to flip this. It'll become times x plus 2 on top, on the bottom negative x minus 1. And this has been flipped so I don't look at it. So where is that 4 going to multiply? across the x plus 2. And on the bottom, the 1 multiplies across bottom doesn't change anything. So what should our final result here be? 4x plus 8 over negative x minus 1. That's acceptable. Yep, that is the composition of the function. Is there a question? Yes.
Yeah, how come you can't factor? Can it help the problem if you factored?
Like left the 4 out? Or are you talking about
Yeah.
you could, it wouldn't, I mean, you could write this, and I mean, that would be acceptable. Yeah.
But it wouldn't help.
It doesn't help us really in terms of determining anything here. Because we're not like setting it equal to 0 or anything like that. We're not trying to find x-intercepts or graph it or anything. All right, so that's the answer to just what's f of g of x. Or no, we're doing g of f of x, right? Now what's the domain? So I'm going to draw my picture again. X first goes into what function? F, and then that f function was what? 1 over x plus 2. And then that gets plugged into g, and we just got that the answer to that is 4x plus 8 over negative x minus 1, right? The f function, I've been writing this below, but I accidentally wrote it above this time, is just 1 over x plus 2. The g function was 4 over x minus 1, right? So what sort of restriction are we going to have on the first step here, from here to here? X cannot be negative 2. Everyone agree with that? X cannot be negative 2. So x cannot be negative 2 because we can't have division by 0 on the first step.
So it has to be the opposite number?
Well, it has to be whatever makes the denominator 0. So I think we're just doing that by inspection, right? Just by visual inspection. You could just set it equal to 0. Just write it as an equation. You know, when is x plus 2 equals 0? Move the 2 over, x is negative 2. If it were more complicated than just x plus 2, you'd just set up the equation. Now, what is it that the g function can't handle? Can't handle a 1, right? A 1 is a problem. But so what we're going to do is we're going to take this function and set it equal to 1, because that's where we would create the issue, wouldn't it? That's what we'll do on all these problems whenever they're like this, all right? So I'm going to set, I'm going to write this up just like I did the last one. We need what? What do we need? That 1 over x plus 2 cannot equal 1, right? Cannot equal 1. And then, so I'll figure out where it does equal 1. So this thing right here cannot be equal to the 1. That would cause the division on the next step. So I go through, I replace the not equal with equal, and then I do this. So clear fractions on both sides, or clear fractions, multiply both sides by x plus 2. The x plus 2's here cancel, and we're left with 1 equals x plus 2. And then subtract 2 on both sides, and you get x is negative 1. But x can't be that, right? X cannot be that. So over here, x cannot be negative 1. So how would we write that domain in interval notation? Negative infinity, negative 2, union, right? Okay, so. Yeah. So who, we do? You look so enthusiastic. I don't want to wake you up. Trying to keep my voice down. That's our answer?
Yes.
Yep, that's everything except -2 and 1. So you can imagine that these could get kind of ugly, right? I mean, you could have some issues with trying to track the domains. If you have some radicals, you might have some issues, right? Like, no, there are radicals in the assignments. You know what? I want you to try and do a problem yourself, like in groups. All right? Same F and G, all right? Same F and G. I want you to find. So let me write what F and G are again so everyone's clear on this. F was 1 over x plus 2. G was 4 over x minus 1. I want you to find f of x and its domain. I'll give you some time, maybe about 10, 15 minutes at the most. Let's do this on a separate piece of paper that you'll turn in for some sort of credit. Yeah. One paper per person. So I've changed things up on you a little bit. F of f. I mean, what does f of f mean? You have to write it out and then do your algebra, figure out your domain. I'll give you a hint. You don't use G. All right? That's about all I can tell you. If you get this one and you want to add a little bonus to what you turn in, like if you get this real quick, then you can try the same problem for G of G and its domain. So this one is bonus. So let's see how much you can get done in the next 10, 12 minutes.